In question 3, it's mostly a circular motion question, and there's a bit of suvat stuff at the end. So the photograph on the right is of a chain swing ride in the amusement park. The disc at the top of the ride is rotating in a horizontal plane, so it's going to be horizontal circular motion we're dealing with. People sit in seats which are attached freely by inextensible chains like 4.3 to a point on the disc. The chain attaching seat A hangs from point X on the ride and makes an angle alpha with the vertical. X is 3.5 from the axis of rotation, which is the vertical line PQ. Okay. As shown in the diagram, the chain is free to swing in or out relative to PQ, moves at angular velocity omega, and is 6 meters above the ground. Okay, so the first thing we have to do is draw a diagram showing the external forces on the seat. Now, I'm actually going to change to a blue, just because I like to draw my components in a different color. So I'm going to slightly copy this diagram. So we're going to isolate seat A. So it's going to come down like this. So this is seat A. Now, A, we're told, or A doesn't have a mass, so we're going to have to do it generally. So we'll have a mass directly downwards of mg. We can split this up to components if we wish. We can find out what the angle is because this is alpha to the vertical, and so these would be similar triangles. So this is alpha to the vertical. And you're essentially switching these around. I think. It's not like it matters because we have alpha here even. It doesn't really matter. It doesn't matter because we don't actually we don't need the components of the velocity, funnily enough, in horizontal circular motion. You can actually do without them in most cases, and it looks like in this case you can. But anyways, so this will have a tension in the string here, or a tension in the cable. The cable? Chain even. Tension in the chain. Now this would be, because it's opposite, that would be T sine alpha. And this is adjacent, so it would be T cos alpha. And then of course it would be spinning around this way with an angular speed omega, which isn't a force, but I should probably include it anyway, just for the diagram's sake. And this is of length 4.3 meters. Cool. Now we're told to find that omega is root g tan alpha over 3.5 plus 4.3 sine alpha. So we have to remember 2 laws of horizontal circular motion. So the first one is that the forces up is equal to the forces down. Now the forces up is T cos alpha and the forces down is mg, so they have to equal. So T cos alpha is mg. Second equation is that the centripetal force inwards, or so force centripetal, is m or omega squared because we're looking for omega. So the inward force is T sine alpha, and this is equal to m or omega squared. Now we're going to leave or there just for a minute, as it is. So we have T in both of these. So if we write T here as mg divided by cos alpha, and we put this into here, we get mg over cos alpha times sine alpha is equal to m or omega squared. So the m's cancel. From trigonometry, you should remember that sine alpha over cos alpha is tan alpha. So this is g tan alpha is or omega squared. So we actually have the g tan alpha part of it. But how do you get 3.5 plus 4.3 sine alpha? Well, if you can imagine this swing sort of going in and out, the distance from P to X is a constant 3.5 meters because it's not like the hinge point is moving. The seat will move, and it will move, say if it moves out this way, the value of sine alpha will get bigger and bigger. So we actually have a component of sine alpha working on the radius of motion. So this length here would be 4.3 times sine alpha. So r is 3.5 plus 4.3 sine alpha. So therefore g tan alpha is 3.5 plus 4.3 sine alpha omega squared. Dividing and taking the square root, we get omega is plus 4.3 sine alpha and the square root. This is positive because clearly you can't have negative radians per second. So I'll just write QED. Now, we have to use dimensional analysis to find the units, or to show that the units are compatible. Now, the units of omega are technically radians per second. However, radians as a unit is naturally dimensionless because it is essentially just the ratio of the length of an arc over the radius of a circle. So the units of omega are actually in just per seconds. So we have that per seconds equals the square root of, now g is meters per second squared. Now, this 3.5 plus 4.3 sine alpha is a substitution for r, which is units of meters. So these cancel. And this gets s to the minus 1, is root s to the minus 2. So inverse seconds is inverse seconds, QED. Cool. Now, it's found by measurement that alpha is 25. Calculate how many complete revolutions the ride makes in 1 minute. Now, there are quite a few different ways of doing this problem, but the first thing to do is to find omega. So omega is 9.8 tan 25 over 3.5 plus 4.3 sine 25. And this is under a square root. So let's put this into the calculator. So square root 9.8 tan 25 over 3.5 plus 4.3 sine 25. You get omega as 0.927. 927 per second. Now, a key formula to know that isn't in the log table, well, it kind of is in the log tables, but you can do this multiple different ways. So, the time for one revolution is 2 pi divided by the angular speed. So this comes from the fact that omega is theta over t, and then rearranging t is theta over omega. Obviously, for one complete revolution, it is 2 pi radians, and t, we're just going to change the capital T for the periodic time. So the time for one revolution is 2 pi over 0.927. Which is 6.778. I'll do it to 3 decimal places like this. So it's actually 3.777977767, a lot of sevens. But yeah, so 6.778 seconds. Now, in 1 minute, so 60 seconds per minute divided by 6.778. So I'll just write this as revs is 60 divided by that. So 60 divided by 6.778 means that the ride makes 8.85 revolutions per minute. Or thereof. Now, this is the suvat part of the question. A person sitting in seat A throws a small orange into the air for some reason. The person imparts a vertical velocity component 4 meters per second to the orange. Calculate the time from the orange is thrown until it hits the ground. Okay, so we have to remember that we're actually 6 meters off the ground. So this is ground level. So the first part of the journey is when it comes up here, and v is 0. So we're going to have to find the height that it's thrown to and the time taken. So we're going to call this journey 1. Then journey 2 is when it goes straight down again, the whole height. So let's start with the first journey with a suvat table. So initial velocity is 4 meters per second. At max height, it's going to be 0 minus g, and we're looking for h. So v squared is u squared plus 2as. So 0 is 4 squared minus 2gh. So h is just 4 squared over 2g. Or 16 over 2g. Which is 0.8. Now, after this, that's going to be its height. So the total height, so I'll just write total, from the ground is 6.8 meters. So now we have to calculate the time from the orange it's thrown until it hits the ground. So we're going to have to calculate the time taken. So this 6.8 will actually be used for the second journey. Now, so u is 4v0 minus gt. So v is u plus at. So we have 0 is 4 minus gt. So t is just 4 over g. Which is 0.4 seconds. So that's the time. So that's the first time for doing it. So when it's at 6.8 meters, this is when the second journey begins. So the total distance traveled is 6.8. Initial velocity is 0 because it's starting from when v was 0. Now u is 0. We want t and acceleration is positive g. So s is ut plus a half at squared. So 6.8 is, well, that's Newton, so that's 4.9 t squared. So t is just 4.9, which is 1.178. So the total time is just t1 plus t2, which is 1.178, 0.4, is 1.578 seconds. And that is the answer to Leaving Cert Applied Maths Higher Level Question 3.